Started. All right, welcome everyone to another installment of AI BDS1. So, what did we do last time? So, last time we switched from the regression problem, which means we want to predict. So, we are still in the job market on predicting things, like want to see how things turn out given certain features. We call them X, and we want to predict Y. And our goal is to train a machine learning model to do this for us in the future, to have new entities like persons, and we can classify them. Or we can do a regression. So in the regression analysis that we previously had on the list, we wanted to actually predict the number, like housing prices. This was our example. We had the Portland housing market with housing prices in Portland, and the goal was to build a system that could predict housing prices when a new house comes on the market. So we would collect features of the house, like uh, where it stands, like the location. And last time we discussed it also a little bit, what kind of other variables we could have. We used the square meters, for example. We could also add number of rooms and so on. And then we wanted to predict the actual price of the house so we can put it on the market. So the system is there to help us with that decision. So this was like going from the business understanding to the data understanding, data preparation, and then finally to the training. And then last time we switched to the classification task. So this one right here, in classification task, we try to sort, like we can imagine like a sorting hat, like in a Harry Potter movie that says, hey, this is either that or this. So we have our variable, our y variable, our target variable is now usually a nominal variable or variable with a limited domain. So for example, in email it could be spam or not spam. It could be fraudulent. We talked about credit card fraud in the past when we talked about class imbalance. So specifically with data preparation problems like class imbalance, they will affect classification tasks the most. So, and the example we used last time to introduce the classification problem and also to introduce some problems that might occur when we use a classical linear regression hypothesis type onto a classification was that we wanted to detect whether a tumor is malignant or benign. Okay, so to summarize, our target variable y has now a limited domain. Now, when I'm talking about limited domain, in our example, it's binary. That means it can have two outcomes. The tumor can either be a benign tumor or it can be a malignant tumor. Now, what's important to say is that classification can also have more than two classes. It doesn't have to be binary. And at the end of the lecture, we will also discover, or maybe towards the mid of the lecture, I'm not sure how far we will progress today. We will explore how we can do this with multi-class classification. So not only two classes, but more than two classes. So how do we deal with these problems? Can we still use the models? How do we deal with that and so on? But for now, we will stick with our binary example. And something I wanted to mention is sometimes if we have a binary classification, which is the prime example on teaching classification models, we sometimes call them negative and positive class. So what does that mean? So usually we could, like from the get-go, we could see, okay, both of the classes are equally important. So we want to equally say, hey, want the model to be equally good in predicting the negative class, the zero, the benign tumor, and the malignant tumor. Sometimes, however, we are very much interested in one class being more favored by our prediction model, meaning that the prediction model should put more effort into detecting this one. So for example, here we could argue that we might want to focus more on the positive class. That means that the model should not miss malignant tumors. That, of course, comes at a cost, which we will speak about in the evaluation section either today or at the beginning of the next lecture. So very important that not at all times are the classes like the same from the weight they carry. So another example is fraudulent transactions, right? And fraudulent transactions, and this is tightly connected to the problem of class imbalance. If you remember, like fraudulent, yes, no. When we look at the distribution of the target variable for fraudulent, right? So we have yes and no. So fraudulent, yes, fraudulent, no. We have a lot of non-fraudulent transactions, right? So the number of non-fraudulent transactions compared to fraudulent transactions is very high. So we call this the majority class and this the minority class in the context of the problem of class imbalance. Like imbalance means that, as you can see here, one class is overrepresented, called the majority class, and one class is highly underrepresented, called the minority class. So with this context, right? With this context, it would be, we will see this in evaluation. There could be a problem if we just let the model train as it is, right? Because it will just learn the no class and it will still come up with like 99% accuracy, which is one of the metrics we will learn, accuracy or ACC, which is one of the metrics how we can like evaluate models. How good are the models? And this is a problem. So we learn how to fix it, what other metrics there are. But these problems usually arise in classification, right? So because in classification, we can easily see this. However, what I wanted to stress out, so this is a little bit of a side note, but it could also be very interesting for you because at some point you want to put this into practice. Now, when you have a regression task, right? So let's say you have a regression task, and usually your training data, I'm talking about your training data or all the data you have available. So this could be considered either all the data or the training data. So the distribution will look, if we do nothing, like if we don't apply techniques that we have learned, like SMOD or like we put we oversample the minority class or we undersample the majority class. These were like two or three things we could do when we have class imbalance. We learned this in data preparation. And if we do nothing, then usually this will turn out pretty bad. And in regression, we might not see this because this is pretty clear. We have only two classes. We see this at once. We see the clear image here. In regression, something similar could happen. It's not called class imbalance there because our y variable doesn't have classes. It can take any value, like on this axis, could potentially take any value, like the housing prices could potentially be any value, right? So we don't have like two housing prices only. And the problem here is that it could be that some combinations of X and Y are very, very rarely appear. And so this is not the same problem, but it's a related problem that we have to fix in training is where we have some combination. So now it's rather a combination than a class. For example, we have housing prices, right? If Y is, let's take the housing price example. And this is like square feet, our square feet, right? Or it was like something like this, our square feet. This was our X variable. So this is Y, this is X. And so if we train the model, for example, in that kind of area, right? So we have like a lot of points here, for example, and we train the model based on this, right? We might have a point here also, maybe a point here, but the majority of points are here, right? That's a similar problem because the model will use all of these data points and the model will think that this is the rule, these are the decisions it is supposed to learn. And it will probably forget about some of the points that are here. And it might be that the behavior, for example, here is rather linear, right? So we would appreciate a nice linear regression model here. But here it could be like exponentially go like this, right? So suddenly the behavior here would be more like this. And now if we predict a new house, right? So we want to predict the house that is like here, that has an X value. So let's call it X, this star. Like if we continue to use the red line, I'm gonna just prolong this. If we continue to use the red line, it would rather be, so it would be here, right? It would be somewhere here instead of maybe somewhere here. So this would be actually the true point we want to predict, right? So it would be somewhere here, but instead now it's somewhere here. So the error would be quite large. And this is because this is underrepresented in the training data set, right? So I just want you to know that a similar thing, it's not called class imbalance because we have no classes, but it's always important to see what your data is trained on. So this is basically out of the knowledge of the model, right? So, and by the way, while we're at it, you can observe the same thing because, I always stress that we have learned the basics of machine learning. And you might know, yeah, we have applied them to linear regression, and now we will apply them to what's called logistic regression, which is the thing we will continue today. However, the same the same problems arise when we have much more complicated models. Like when you look at ChatGPT, which is based on a transformer model, which is a deep learning model, more specifically a neural network. It's it's a form of artificial neural network, very complex, many many building blocks, and we will learn about this in the next semester. Many building blocks. However, at the core, it functions in training. It functions the same way. So um, this right here, and I think there was a question somewhat in the middle of the lecture series, and I think I haven't quite answered it yet, and I think this is the right time to answer, where someone asked, hey, what about cases that are outside of it? And so we have this phenomenon where it drives towards the middle. So everything what generative AI does is driving towards the most the things that are most represented. So when we talk about words, it might not have knowledge about some edge case formulation, some aspects, maybe some, for example, when you have like some deep Bavarian culture, for example, or some old recipes, the model will probably fail because it's here. It's somewhere here, and it will assume that it actually comes from the body of the training data. So if tokens, which can be words, like it could be sub-word level, but let's say they are words, if tokens are underrepresented, they will not be spit out frequently, and it's harder for the model to determine. So everything moves towards kind of an average. The same as when we let Gen AI generate music, right? When we let Gen AI generate images, you might have seen the funny images when you like want to have an average person, but the average person looks like a supermodel. That's because these images are overrepresented in the internet. Like we have, believe it or not, the internet is full of like it's like a shiny world out there sometimes, right? And the reality sometimes gets locked up, right? So and this is basically the same problem that we have here in this very simple linear regression. This also happens with much more complex deep neural networks, right? So being aware of these problems, like the parking lot problem, where the parking lot is not maybe representable, or where the true process changes somewhat at certain levels. For example, it changes from here, and we have no knowledge of this realm, or we have barely any knowledge. The model will always be overrepresented by these data points, right? So it's a similar problem to the class imbalance problem. And this is where we want to return today, to the classification. All right, so we want to return to the classification. And so the first thing we tried last time is we tried to actually apply like a linear regression to this. And we found that there are some problems with it. First and foremost, like the X values, they don't really bother us. We have tumor size. Tumor size is a normal numerical variable. It can take on basically any value. So we don't bother with that. However, our Y variable now can basically only take on two values, yes or no. However, our model should have a tendency to either 1 or 0, right? So to either yes or no. So we can live with having like this range between 0 and 1, and the model giving us an idea, like is the number, for example, closer to 1, we would assume that the model would be in favor of saying, yes, this is a malignant tumor. And if the number is closer to 0, we would say maybe the model prefers to say, hey, this is more like a benign tumor, okay, or a non-malignant tumor. And so we said, okay, we can basically solve this if we have like a threshold that we set. So usually the threshold, yeah, I say we set the threshold, but usually the threshold is in the middle, which makes sense. So we give the model equal chance on expressing a tendency. However, with the linear regression, we have several problems. Now, in linear regression, we cannot force the linear regression to stick between those two values. It's simply impossible because, like, it's a linear hypothesis, as you can see here. So any value here can express any value here, right? So there is no, like, we don't compress it to 0 and 1. And this has some problems. So the first problem is between 0 and 1 is the problem, and this can be affected by outliers like this one right here. If we have an outlier like this one, it will drive this. Let's make it in. Let's use other colors. So let's do this in blue so we can see. So this one right here would be the original, right? This would be the original regression line if we use a regression. And if we take into account this point right here, right? If we take into account this point right here, it could potentially be this line right here, right? So this line right here, which is a problem now because it's a different line, and it will you can see right away that this will be rather worse, right? Because now if we have the same threshold, if this is the threshold here, right? We can see how this changes. So we can see if this is the threshold, we can see that this line goes over the threshold right here. So basically everything in this realm will be classified differently now, which is a problem, right? So this could even be worse if the outlier is more far apart. Okay, so our idea was, okay, we want to find something that actually limits our model to have outputs between 0 and 1. So basically, we are looking for a function that compresses a potential infinite from minus infinite to plus infinite feature input, right? Or a linear combination of features, because usually we don't have one feature. So we have a linear combination of features like this one. This is a linear combination, like this is up, up, up. And we have the number of features times xn. So we have n features, n columns that we use. And this will be, and so this linear combination, like we need to limit the outcome. So this could be potentially any number, and we can of course not change this, but we want to map this to this output. We want to map it to a number between 0 and 1, so we can better apply our thresholds. The threshold should be in the middle, and we can understand what the tendency of the model is. Like, for example, is the number 0.89, so we know it's a tendency towards 1, or is it like 0.21 and it's a tendency towards 0, which would mean this is a benign tumor. So what we do is we just find a function that does that. And it's as simple as this. So this is also called sometimes the search for such a task. So basically this is the task, right? This is our task right now. So we act like we act like the logistic regression has not been discovered yet. So this is our task. So we have to find what's sometimes called a link function, right? So this is exactly what it does. It links our feature inputs, like this one right here, like the linear combination. It links the linear combination that we have. So this is called a linear combination. It's basically just all our variables that we want to consider. Like in the basic event, we just have one variable, and we could show this with one variable. But usually, of course, it makes no sense teaching it with one variable, because usually we will have more than one variable, like in the regression model. We already discussed that having only one variable to predict the housing price is a little bit fishy. So the same, of course, applies for classification. We want to put in as much information, as many pieces of information that we can. So we are looking for a link function, and we find a link function that is called the sigmoid function or the logistic function. It's different names, same function. And it's that function right here. This is the function, right? So this is like a little bit of math, but what it actually does mathematically is what we're looking for. So we're just having a function that does exactly what we're looking for. It compresses a potential minus infinite to plus infinite, like Z is our linear combination right here, because this is a number, right? You have to imagine, like this is basically a number after I apply it, right? After I have my parameters fixed, this is a number, right? So this is Z, right? So Z is my linear combination. That's it. So, and this is a number. I can calculate this. After I have my parameters, I can calculate theta 0 is some number, let's say 2, and then plus 1.5 times 1.5 times tumor size, for example, 1.5 times tumor size, and then maybe another variable plus theta 2, maybe plus 0.25 times age of patient, okay? And then I get a number because I can calculate it. These are all numbers. So I get a number. Let's say I get a number 1.3, right? Then I put the number 1.3 into here, like into this. So this is Z equals Z, right? So I put the number in here, and then that's it. And then I just calculate my Y value. And the Y value now will always be a number between 0 and 1, and that's it. I don't want you to think of this as any magic or any maximum likelihood thing, or it's just a function that does the job we are looking for. We just take the disadvantages of the linear regression and we try to fix it by using another link function, by just using another function that connects them. So basically, we put a function around the linear regression. So basically this here. So if we put away the g here, that this is the linear regression. Like if I put away the g, that's the linear regression. That's the formula for the linear regression. That's our hypothesis form of the linear regression. And now we have a new hypothesis form, right? So a new child to train. So the child is a little bit different now, but we still will undergo all the same steps, just that the child is a little bit different now. We still need to find the parameters. It's always the same. We still need to find the parameters. We still have a cost function. We still compare in the cost function the true values to the output of our new hypothesis type. Everything is exactly the same. Just the form of the hypothesis is different. And this is really important. And I want you to acknowledge that, right? I want you to imagine that we don't like this is not a different world. This is not like a different approach. It's the same machine learning approach. We just have to cater a little bit more to the problem. So this is why it's important that you, at the beginning, determine your business understanding, saying, hey, what kind of task do I have? And do I have a classification task? Okay, I have a binary classification task. Okay. Now I know I would not use linear regression, but I would rather use something like logistic regression. Of course, there are other things you could use. You could use XGBoost, support vector regression. You could use neural networks, and we will learn about neural networks. You can basically do everything with neural networks. It doesn't care if it's a classification or regression, doesn't really care. So that's the beauty of it, but it also comes with some downsides. But in the logistic regression, we just use a function g, which is that function, right? So this is our new hypothesis here. And the function g, of course, is this, like g of z is 1 divided by 1 plus x to the power of minus. Don't forget the minus, please. Like you could potentially calculate in the exam something. Please don't forget the minus, right? So if you have like a node ready, just do this here. Like, don't forget the minus, please, okay? This is a common mistake that people forget the minus because they just calculate, they use all the time. So if I were you, what I would do, simple as that, I would do it in 2 steps. I would first calculate Z, which is just a linear combination. So you just calculate this right here. So just what I said, you calculate, if I have some values, you calculate 1 plus 1 times 3 times, this is the tumor size, times 20 plus then there comes the next parameter, 0.25 times 15. And then you calculate this first, and then you get a value, set, and then you put this into the equation. Okay, do yourself a favor, do it like this, and you'll be fine. And also you can write 2 lines in the exam. So if you get some of this wrong, you will at least get some points. But we will talk about the exam next week. So these are just some pointers I will give you right away to make it easier for you. So now that we have our link function, so now that we have our new form of hypothesis, and this is of course called the logistic regression model. So this form of hypothesis is called logistic regression model, whereas the other form was called the linear regression model that we apply to the housing prices. Please don't be confused by the word regression here. Now, something I want to make very, very clear is that there is a regression problem where we predict like real numbers like housing prices, stock price, and then there's a classification problem. The logistic regression is called logistic regression model, but it's a classification model actually. It's applied to classification. So this is something where your brain might explode. However, this is historically, as we like to say, this has like grown historically, okay? Because you might also know the logistic regression models way before machine learning. But it's better to have say, okay, we have a classification or regression problem, and then for these problems we can use specific hypothesis types. All right. So and now the question is, like in the linear regression, it was pretty easy. Like we had our y, we had our hypothesis value, and then we had some parameters. Like for example, what was the parameter in front of the square feet, right? And we could say whatever this parameter is. So for example, this parameter is like 2.5. We know, okay, the higher the square feet, the higher the selling price will be. And it will be higher by this factor. Okay, it will be higher by this factor. And this here acts as sort of a baseline price, like when there's actually nothing. So this is like a baseline price, and then we add a price premium that is based on the actual square feet. So it makes sense that if we have like larger room available, that the price would go up. Okay. So when you interpret these, you can easily make sense of this that way, right? Because, and why can you do this? Because there is a direct connection between this. So this is just, you see, this is the equal sign. So there is nothing in between. So there's a direct connection. So it's fairly easy for us to see the influence of one factor. And now here, we also have a direct connection, but it's kind of masked by this function, right? So how can we interpret the output, right? Sorry, the output of this classification model. Now for the regression, I just showed you how we could do it, and I think this is intuitive, but neither way I wanted to have this comparison. And now here, what we have is our value, of course, our hypothesis output is now between 0 and 1. Why? Because we wanted it that way. This was our goal all along. So this will always be, this output here, no matter what, will always be a number between 0 and 1. And then we get a value between 0 and 1. For example, we get 0.7, right? And in our example, we said, okay, we have the negative class, which is represented by 0, so the lower end, and the positive class, which is 1, which is that the tumor is malignant, right? So we call it positive class, but to be honest, it's not really positive because having to know that the tumor is malignant is not positive. However, we call it that way. So a number close to 1, here a number closer to 1, will actually say, okay, there is a high probability that this tumor is malignant. And you can like sort of interpret this as a probability. Let me say some words about probability. Probability is a thing of statistics, right? We use probability in statistics a lot. So this is why these things here are fairly important. So I actually don't want you to think of this as a probability in this special case because of the construction of the model. And if some underlying statistical things are correct, this is an actual probability, like with all the math behind it. Like there's a sigma algebra, blah, blah, blah. It's between 1 and 0. And all the conditions for this to be a real probability is fulfilled. Like not every number between 0 and 1 is a probability. There are many things that have to be considered here. And you've learned this in statistics, or you may not have learned this. But as I said, in machine learning, we don't really care about the statistics things. Like we will care about them in more advanced applications. So I'm not saying this, I don't want you to hate on statistics, but for now, I would like to keep it separate so that you get the idea of machine learning as a different concept. So we can interpret this as a probability, but I want you to not really think of it as a probability, but rather as kind of the confidence of the algorithm towards one or the other decision. Like I want you to see that if an algorithm says 0.99, the algorithm is fairly sure that the tumor will be malignant, right? And if an algorithm says 0.08, for example, the algorithm is fairly sure that the tumor will be benign, okay? So this is how I want you to think. Now, this is what the algorithm says. If the algorithm is bad, then this doesn't really matter, and we will see an evaluation. However, this is the output. And then what are we doing with this output to give a final answer? Well, it's simply as that. We're just gonna decide if a value that we have, for example, 0.7 is larger than 0.5, So since our original y variable here, our original y variable can only take on two values, we will just simply say, okay, it's larger than 0.5, so we classify it as malignant, right? So, and that's basically one of the of an interpretation that you can have. But I would prefer like you give it as sort of a direction, sort of a confidence of the algorithm, okay? All right, so now that we've had this, let's have a look at how this behaves. So this is fairly easy. So we just want to see when do we actually get what. Now in a binary classification, it's always the same. We have two classes. We have 1 and we have 0 right here. Okay, so this is always the same. And we have a threshold, which is that, and the threshold is of course 0.5, right? The threshold of the y variable is 0.5. So this is the threshold. So basically, it's fairly easy. Like in this case, for example, we just look if the function, right? If our function is larger than 0.5, like for example with the 0.7, that this means that we can classify it as 1, right? And if it's smaller than 0.5, like in this case, we classify it as 0, right? Or as whatever this class is like. In this case, we coded it as 1 or 0, but you can also say, okay, this is like malignant and this is benign, right? Okay, all right. And now what we want to look is, so this is the first line here. These are the first lines, and this we already know, right? And now the question is when this happens, right? So the question is when does this happen? So how does and when I say when, it's obviously depending on our input variables, our features, as it should be. Like we put features in our model and then we want a reaction from the model. So how do these features behave? Must behave in order for our model to behave either towards 1 or towards 0. And it's fairly simple. You can see, okay, here, if z is positive, so if this is a larger positive value, it will be classified as towards 1, right? As you can see here, this is just what the function does. So the larger z gets, the more it approaches 1, the value of 1, right? And now the smaller z gets, so if z is basically smaller than 0, then it will be classified towards 0, right? So that's it. That's like how it behaves. It's pretty simple. Now, a short question that always comes up at this point is, yeah, but what if it's exactly 0.5? Well, you have to decide. You see, you can put the equal somewhat here, right? So it depends. So if I put the equal somewhat here and somewhat here, I say, okay, I include the exact value of 0.5 either towards the positive or the negative. It's your choice. Here I've made the choice for you. So we have greater and equal 0.5. So if it should be exactly 0.5, we will count it towards the positive class. However, right, and this is what I'm asking you now. When you have, like, you apply a logistic regression, and I want to use this topic because it's a rather sensitive topic. Cancer is a horrible disease. And so I want you to think, like, let's say we train this model, and we have a model output, right? And the model output is, I'm gonna make it easier for you, so don't this edge case in the model output is 0.51, right? And you know where I'm going with this. You definitely know where I'm going with this. So let's say you get this and the physician says, okay, I have this great AI-based tool, and the AI-based tool says this is the value, right? And technically, we would say now this is malignant, right? Based on our 0.5 rule here, based on this rule right here, our threshold, right? Now, how do you feel about this? How do you feel about this? Specifically with that value. Specifically when I told you to treat it more like a probability or a confidence, like you can choose whatever. It's like, how do you feel about this? You could put it in the chat. There are no wrong answers. Like I'm just I'm just asking because we also want to, like, as I said in the beginning, train you a little bit to be sensitive towards also human AI interaction. Because this will affect people. This will affect the doctor, that is the user of the system, but there's also another stakeholder, which is the patient, and is even the patient is heavily affected, most affected, way more than the actual user of the system. That is the doctor, right? So you always need to, like, when you build a system, always need to, like, care for this. So it could be that in these cases here, right? In these cases here, there is like a gray zone that we build in. Like there could be a gray zone that we build where we say, okay, in this case, we'll have another run. We will let other people look at this again. But yeah, I want to know from you, how do you feel? Because we will see that this doesn't now. This is assuming that the AI model is very good, right? We will know what happens when the AI model is not good in evaluation, but assuming that is very good, what would you do here? Like, what would be your reaction if your doctor tells you, hey, I used an AI tool and the AI tool can spit out values between 0 and 1. If it's close to 1, the tumor is highly likely to be malignant. If it's close to 0, it's highly likely to be benign. And then the doctor says, my AI-based decision support system says the value is 0.51. How do you feel about this? Like, don't be shy. We need to discuss this. It's an important part of building systems. It's also, who do you build it for, right? So it's not only teaching you how this works, but also showing you the implication that this small thing, we're not into ChatGPT or any complex models. This is just logistic regression, but it doesn't matter. It still has these kind of repercussions. Although this is a very simple model, there's nothing hard in like this equation or anything. Now, how would you feel about it? I could also make the question easier for you and ask you, um, what would you do? Would you follow the advice? Would you get a second opinion? Probably not very different from before the test because it doesn't really tell me anything. I could simply, yeah, exactly. So you're not sure. Like you don't have any, like the level of information, or let me rephrase it. The What you feel is you have a feeling of uncertainty, right? And your level of uncertainty doesn't really go down with this, right? So this is probably best expressed, like Gina said, like you don't really know much than before. So I'm gonna give you another value, right? So your physician says the same thing, like says, hey, I used a very good AI-based tool. Um, the values can be 1, and if the values are close to 1, it's malignant, and if the values are close to 0, the system tends to have the idea that the tumor is benign. And now the system gives you the value of 0.08. What would you do now? Do you feel better now? Ask yourself, would you feel better with it? I mean, how would you feel? I just want you to know, because this is how it works. AI systems are not isolated, like in the credit card fraud or in some insignificant things that do not affect maybe human health, so even maybe easier than credit card fraud, like spam email detection, right? But how would you feel about this compared to this? So what I'm aiming at is, do you feel much different? Would you feel much different? This is my question. The model is somewhat confident, so it gives us information. The model always gives you information. This is the job of the model. So, but I know what you mean. So my question would not be what the model does, but how you value the information. So, the model does what it does, right? So my question is, how do you as a human value the information? So this is not like an exam question or something. It's about how you feel about this, right? This is what I want to know. I want to discuss this with you because this is the correct point to discuss this. And there is time for that in the lecture. because if we have more complex models, it's not that easy to see this mechanic, to see the gray space right here. It's fairly easy to do it here. I would value this more because it is like 9% certain that it is zero. The model, yeah, the model has a certainty. Yeah, has a certainty. You would value this more. Okay. Okay. You would value this more. Okay. Are there any other opinions? You can also say what you would do. Like, would you get a second opinion? Would you say what would be your answer just to that be? Like, how would you feel? Like the alternative is just that the doctor says, okay, the doctor just says the tumor is benign. So the doctor sees this, doesn't tell you anything about that, and says the tumor is benign. So is ignorance bliss here? So we don't have to like deepen this discussion, but when you leave the lecture, I want you to think about this. I want you to deeply think about this because all we talked about this is uh like human AI interaction, but actually it's also like we have another stakeholder, right? Which is you, the human, like the patient. And you don't have any, basically, in this case, you don't have any interaction at all with the AI. You have only interaction with the doctor. So the human AI interaction is between the doctor, right? So this is the doctor, this is the patient, and this is the AI, like the computer. So they interact with each other, and the doctor can tell you what the AI said. So your only interaction is like an information. You don't really interact with the AI, but the doctor gives you basically an information. So this always goes through the doctor, right? So there is no direct connection. Okay, let's see. Um, I would probably still ask the doctor for his opinion because I don't actually know how good the AI is. Yeah, this is a thing I was kind of waiting for. Like, you don't really know how good the AI is. Like you just like this is your case. Like, how good is the AI? So the question is, what would make you more confident in the AI? The difference between and is huge. In a negative situation, we diagnosed with cancer like this, one would be more loss averse and would prefer to focus on having a higher chance of survival. Oh yeah, it's also definitely a problem. Like what I could have like the third option where I said it's 0 point, whereas this, right? I intentionally not to ruin your day choose this one, but yeah, it could also be this. And yeah, of course, you will react different to this than to that because we know that we've studied economics, so we know that this is not that we are not indifferent. We are definitely not like it's not the same. Yeah, we know prospect theory, we know loss aversion. So we definitely know that we would react different to that number as that, like neutrally seeing that this might express the same confidence of the algorithm. Yeah, but I think an important factor is um, aside from what Lynn mentioned, is what Gina mentioned when she said, I would probably still ask doctor's opinion because I actually don't know how good the AI is or how it came to the decision. Yeah, so two things here, two things that she mentioned is the first, we don't actually see how good the AI is. Like, for example, we just know, hey, the doctor just said, hey, I asked an AI, right? Um, so it would be important to see this in action, like to see, okay, how many cases, so to present real world cases of real patients that the AI has helped to predict and probably see, hey, is this good? Is this bad? And maybe also what would help is say, hey, some doctors would have predicted these cases wrong, for example, right? So actually, like showing like hundreds examples where the AI was better than the human, like this would maybe help, right? But uh, judging alone on that number, right, is not it. And this is why I want you to act cautiously when you have like these numbers and you look at local cases. And this is why we, of course, will do the evaluation. However, the patient doesn't get all this. The patient doesn't design the model. The patient doesn't get all the evaluation. Hell, the doctor won't even do. The doctor is a medical professional. Doctor doesn't train ML models. However, the doctor has a lot of interaction with the system and has more than one case. But you as a patient are the one case that's important to you, right? The doctor has many cases and can say, okay, in this case, the AI was fairly good and better than my colleagues, maybe. So the doctor has accumulated experience in his or her interaction with the AI, right? But this, you don't. You simply don't. You have no history of how the AI reacted to different cases. Also, another point that Gina mentioned is how good he is and how it came to the decision. So, what kind of variables were taken into account? Now, the problem here is that this might help if you understand the domain, but again, you don't understand the domain. So that for the doctor, an XAI approach, or basically we don't need an XAI approach because we actually have the parameters right here, but let's call it XAI because just saying, okay, we explained the decision somehow. We said, okay, your plot, your plot values and this CT, this area on the CT, the AI took into account, and this is why the AI decided that the tumor was malignant, or said, okay, the tumor size is very large, so it grew a lot. It was aggressive, so it usually this is a malignant tumor. But you don't have this knowledge. You don't have the domain knowledge. Usually, you are not a doctor. You did did not go through 10 years of medical school, right? 10 years plus if you count like higher qualifications. Um, and you can see where I'm getting it. I'm just using this simple example to show you that there is more to designing AI-based decision support systems. You have to think of the people. Like they can be technically, they can succeed on a technical level, but they also need to be accepted, right? They also need to be like people, you need to show the people that they are actually really good because the stakeholders are not the same, specifically in this case. As I said, the patient has no interaction with the AI other than what the doctor tells the patient, right? So I think this is rather important. So of course this was optional, right? So this was optional. This was an optional discussion, but it was a fairly important one, right? So and it was at a good place. Okay, all right. Now, and I want you to think about this. When you leave the lecture, think about this. Hey, is this really good? And how could we maybe improve this? What would it take for me to trust the AI system more? So these are the questions you should ask yourself. Okay, then Lynn just said, is it true that according to Bayes theorem, it's still possible for this probability to be incorrect? So not, I wouldn't put in Bayes theorem and probability. So as I said, I urge you not to think of this as probability because thinking of this in probability makes it somewhat sexy. It makes it someone say, okay, as it was like counted, for example, who said that? Yeah, so M, I don't know what his or her name is. I would value this more because it's like 22% certain that it is zero. It's not. This percentage. This is a thing we use this probability thing. We use this probability thinking, and probability equals risk. Like we want to reduce risk. We want to reduce risk and we want to reduce uncertainty. Now, risk and uncertainty are two different things. Uncertainty means we have no information. Uncertainty means we have no clue, right? We have uncertainty. We have no clue, right? These are different situations. And risk situation under risk is we have somewhat, we have probability. Have probability. We have probability. So if we treat this as a probability, we will go from an uncertainty to a risk situation, and our decision behavior will be vastly different. Because we might think that actually we have something like 92%, right? And sure, but it's actually an algorithm. So all the factors that Gina said, they also play a role. Now, how we would need a probability over the probability. So how sure can we be that the probability is correct? And you will never get this probability. This is not something we could get, right? And this is why I want you to get an understanding And so the whole probability thing is not really what we're aiming at. We're aiming at making good predictions and then like finding out how good the predictions are, and then retrain the model with real world cases where they actually had cancer and it was like where they actually had cancer or had no cancer, right? So um, this probability be incorrect. So first of all, don't treat it as a probability. In this case, it is a probability, so it's not wrong to do it. So I cannot say you don't do it. You can do whatever you want, but I want to urge you not to do it because in an ANN later, when we use ANN later, and we use it for the same task, we could use an ANN for the exact same task. Like the ANN can also put out values between 0 and 1. Like in an ANN, this will also be, if an ANN spits out 0.08, this is definitely not a probability. This is just this, we treat it, but you will treat it as one, right? And so you will go from uncertainty to risk, which is not true. You're still uncertain because you have so many question marks about this, about the model itself, about how trustworthy this is. First and foremost, is the model great? Did we collect all the information and so on? So how correct is this? We don't know how correct the 0.08 is. Like if you treat this as a probability, you basically act as if this is a true probability that has no flaws, right? So uh, and what's right or wrong is if you have a malignant tumor or benign tumor. So the underlying event is not a probability. The underlying event is a yes or no question. So you have a tumor and it either is malignant or benign. There is nothing in between. The tumor is not 8% malignant. The tumor is either malignant or is benign. There is nothing in between. This is the real world, right? So we model it and we model it on a scale. We use this between 0 and 1, but in reality, it's either one or the other. That is the reality. This is the reality we model, right? So this is what, and so having this thing right here says, okay, it's maybe more likely to be, but yeah, there could still be a risk that is. So this just means that the model itself is more confident, but we don't know if the model's confidence is justified. We don't know how good the model is. So, and I would leave out Bayes' theorem, right? So, like the Bayes theorem, what the Bayes theorem basically says, it's so frequentist and Bayes view, they come to a probability of they just explain differently how we come to a probability of zero point 0.2, for example, right? Frequentist view says, okay, we do an experiment like infinite times. Okay, this is impossible. The frequentist view is impossible to recreate. We cannot do this. There are rare events that we cannot do. We can not do anything infinite, but we can, for some events, we can't even do it enough times that we would be justified to have it done enough times, right? So, and Bayes says, okay, there's an a priori probability that comes from somewhere, from your feeling, from whatever, and this is then updated by observation, and observation is data. Like this is then updated by our observations. So, for example, if you have the feeling that today it will not be raining, and then you look out the window every hour and it gets darker and darker and darker, this will update your probability of rain, right? So this is how Bayes comes. So it's two views of how a probability of, for example, zero point 0.2 comes. So this is like frequentist view and Bayes, right? But this is no topic for today. This is statistics and probability topic. You can read about it on the internet. But as I said, try to not treat it as a probability. It will be better for you. So yeah, but you see how already this discussion, it was a discussion sparked, and seeing the difference between a model and the reality. So the reality actually here is simpler than the model because we are only it is or it isn't. Now, the reasons that lead, of course, to a cancer are not simple, right? Body is very complex. We don't understand it at all. What leads to it, right? So so catching it all in our Z, which is our feature combination, is rather hard. So the complexity here is in this one, right? In the explanation variable and explanatory variables in the what we call the features, right? Okay, so yeah, but I hope this discussion showed you that it's not all gray and white, and that we have other things also to think about when we build these systems. right? And now, if you want to know, yeah, but how can we solve it? Well, some things I told you, you can, for example, show people how the system works. Like you can show the patient, these are the last 100 cases, and in these cases, some physicians were wrong and the AI were correct, and you could convince them if the AI is actually good because you have the experience, you worked with the AI to actually convince people that this is a great way on backing up a decision. And then, and if they don't want, you can still ask other doctors. You can say, okay, the AI and the other doctors agree and something like this. So there are some things you can do, right? You can have like explainability things like show how the variables influence and how this is in similar cases, like show similar cases to your case, right? Um, and show how the AI reacted there and show how the AI took into the variables the same way as for you so that the AI doesn't act completely crazy when they observe you. And I think this is pretty important. Okay, so there are some things that can be done, but we will discuss about the XAI part in AI BDS2. But you can see you can do this already. Like we can discuss this already. Like my example here, this is XAI, right? It's not really XAI because this model is transparent from the get-go. So it's what we call inherently transparent. So it's a white, we also call this a white box model, right? So this is a model where we have to do nothing. It's just we know exactly the influence of the features. So we know exactly how the housing price came to be. The model used the parameter of 2.5, so we know how much this model values the square feet. We know exactly how the model decides it because this is the parameter. And remember, the parameter are the inner workings of a model, like the child, like we train the child, we train ourselves, right? And so this is exactly it. All right. Okay, so and then I want to go. This is probably the last thing we'll do today. So we do the evaluation at the beginning of next week, and I will also record a separate video because I told you we missed one appointment. So I will record the evaluation video and we'll quickly have a summary of the evaluation. I will probably do this on the weekend, probably. It depends on how far we come today, but yeah. So decision boundary. Okay, this is a concept I want to introduce. Okay, so the decision boundary, and this is something for classification, right? This is something only for classification. Now, to understand the decision boundary, you need to understand the following graphics. I'm gonna draw it very cleanly for you, so we can forget about this for a moment. Let me just enlarge this a little bit. So we always have this nice graphic when we have a binary classification. We can have two variables, right? So the beauty of it, we can have two variables. So let's say we have two variables, right? These are features. Now these are x values. So remember, this is not your typical diagram where we have the y value here, but these are two variables, right? These are two variables. For example, let's say this is tumor size. This is tumor size. And this is maybe age of patient, okay? Age of patient. All right, so these are two feature values. Like, okay, and the beauty is in the binary classification, I can use this. I can use two variables this time, and now our y variable is expressed by the form of the point. So this means that the tumor is malignant, and this means that the tumor is benign. So, okay, so what we do is we're gonna have I'm gonna draw some data points here. All right, so this should be it. Okay, so this is the situation. Like we assume we have two variables, and now the beauty is in a classification, we can use this form because we can just label them, right? So basically, to make sure you understand how I came to this based on the data table, because I love to have the data table view, right? So we have these variables, and y says it's either malignant or benign. So it's either malignant or benign. Malignant or benign. Malignant, malignant, benign. So, and this is why I can just label them because it's only binary, right? So And so I label them and I label each combination. So again, this is an ID. So 1, 2, 3, 4, 5, 6. So for example, this is ID. This point right here is ID equals 6. So this is ID 6, for example, right? It's ID 6 it's a malignant, it's benign. So okay. So this is ID 6, for example, this point right here. I'm gonna make it solid so that you see that this is ID 6, okay? So that you know the relation between the data table and my visualization, okay? All right. And now what we're interested in is how well our model separates the two classes, because this is something else you can think of, right? So we know that the model sorts in either malignant or benign, right? But how good does it separate? And that's where the concept of a decision boundary is, right? So basically, it's a little bit like a regression, but in this case, of course, the decision boundary is that thing right here. So decision boundary says, okay, everything left of this is benign, and everything to the right of this is malignant, right? And the decision boundary can be extracted from the model, right? So it's just a concept to visualize you what a classification does. We don't really draw decision boundaries, so I can ensure you this is not something you have to do. Like I don't have to draw decision boundaries like in the exam or something. Cannot draw anyway because it's an online exam. But I want to show you how this works, and this is a fairly cool concept to understand how we can generate more complex decision boundaries, right? So this is where we're aiming it at. Okay, so let's see. So you can see the situation right here. So we have y equals 0 and y equals 1 here. So it's basically the same I just showed you, but I wanted to show you on a clean idea how we get this, how this graphic comes to life, basically. Okay. So what we do now is, you see, here's my mouse, sorry. So this is the same thing. And now we're gonna have a look at the decision boundary. Okay. So let me just see here. So we have to look at the decision boundary. Okay, so we have our hypothesis. Now I want you to, let's say we have a trained hypothesis. We can only generate a decision boundary with a trained hypothesis. So in my case, this is an example, right? So we have a logistic regression. We have the same case. So we have tumor size, right? We have here two variables. Let's not call them tumor size because they are one. So, but yeah, they can basically be anything. So this could be tumor size, and this could be age of patient. Okay, like I said, we use this example. Okay, so and now let's say we have a trained model, and the trained parameter vector looks like this. This is the trained parameter vector -3, 1, 1. So that means that theta 0, the first parameter, is -3. The second parameter is 1, and the third parameter theta 2 is also 1. Okay, so assume we have a trained model. So this is important. Assume trained model. To be fair, as you know, the training process we said was like on a timeline. So we start with a stupid model and get our nice model. So it could also be somewhere in between, or it could also be somewhere here when we start out. So it doesn't really matter. It could also be a stupid model. Like these could also be starting values, right? So I'm just saying. So it doesn't really matter. So you could also like look at the decision boundary mid-training, right? Because all that characterizes a model, as we've learned, are the parameters. And now we've set these parameters. So basically, this is the idea, right? So this is the idea. Now we want to predict y equals. So what happens? When do we predict y equals 1? Okay, and it's fairly simple. So we're gonna scroll up a little bit. And this is why we did this, right? So we ask ourselves basically, when do we predict 1? So when do we predict 1? And we said, hey, for that, our value right here, like our linear combination, needs to be larger or equal to 0. Okay? So this is the idea. And the same idea. So we're gonna take our Z. So this is this here. This is the linear combination, or what we call Z, right? So this is the thing in parentheses. So right here, so if this is -3, then we have -3 times nothing, right? Plus x1, because this is 1, so 1 times x1. I'm going to make it easy. Plus 1 time, so that you know exactly that I'm just writing it down as I dictated it right here. Okay. So, okay. So we know this. So this that we can take the g off because we know from the behavior that z, if z is larger than 0, like the thing right here in the function, right? This thing right here, this is z. If z is larger than 0, right? Then we classify y equals 1. This is just how the function works, always. This is just how the sigmoid function works. We just use the idea of the function that we have. Okay. And now what we can basically do is we can like formulate this. So we can just like do a little bit, we do the +3 on the other side. So we need, okay, x1 plus x2 is larger or equal to 3, right? And the opposite is true. Now, opposite is obviously true. If we do this, now, and basically what you can do now to draw this thing, if you want to, you can just say, okay, x1, what does x1 equal? And then we can just like throw it up and you see, and we get this line right here, right? So you get this line right here, okay? So, and how do you get this line? Well, it's pretty easy. A small trick to get this line is you can set one of these to 0. So, so what happens if this is 0? If one of this is 0, then that means that it's the least condition that we have is equal 3. So this is the smallest condition. So that means if, for example, x1 is 0, like if x1 is 0, right here, then x2, if x1 is 0, then x2 needs to be actually 3. And otherwise, if x2 is 0, then x1 needs to be 3. And then we can draw any combination of the two, then fulfills this equation. So x1 plus x2 needs to be 3. Okay? This is the decision boundary. For everything to the right of the decision boundary, be y equals 1. And of course, the opposite goes for the y equals 0, everything to the left of the decision boundary, right? So we can see that we can actually generate the conditions from the model, right? And of course, our parameters, they characterize the model, so we can actually usually we cannot visualize this because we have more than 2 variables, but I just wanted you to show that this is a decision boundary. And now we're going to move to, this is actually not the reason why I showed you this because, yeah, well, that's pretty easy. But now I want to show you that we also can do, and this is a misconception usually, we can also do non-linear decision boundaries with that, right? So we are not constrained in any of these easy things. We can also do something like this here, right? So same idea, we have x2, we have x1, right? It's the exact same thing, and we label them, okay, here, this is y equals 0, so benign tumors, and the red axis are the malignant tumors, okay? So that the data situation looks different now. And if we look at this data situation, this is called non-linear separable. So we cannot separate them. You can try to put in a line here, and you cannot separate the axis from the circles in any way using a linear function, a line, right? So it's not possible. So, and now what we're going to do is, and what you see here is that, okay, we have our model. Again, we use G, same function, same link function, always the same. We use logistic regression. However, we add some more. We do some feature engineering. So this is normal, like we have tumor size, nice. We have the age again, okay. And now what we have tumor size squared and we have age squared added, right? And so we just decided to add this. We might have decided to add this in a pre-processing step. We might just add it right here. And I will talk a little bit about why do we add this? How do we get this? How do I know this? What What are all these things you do? And I will explain it in a second. But we will see it when we look at the decision boundaries. So for now, if I would train a model, if I would train a model on this data set, it would probably set the parameters like this. For example, theta 0 is -1, theta 1 is 0, theta 2 is 0. So basically, the natural version of these variables have no influence. However, theta 3 equals 1 and theta 4 equals 1, right? So the squared versions of these are more important now. So if we want to interpret this, right? So you can see that we can also directly interpret this. So 0 means no influence, right? And larger numbers mean more influence, obviously. And then, of course, the plus and the minus also. So this is the direction of the influence, and this is the magnitude of the influence, right? Obviously, like in the linear regression. So, and now, if we do this, we can do the same. Now predict y equals 1. We know, okay, z has to be larger than 0. Okay, so it's the same. So we write down the same thing. So we have -1 plus, this is 0 plus 0 times x1 plus 0 times x2, which is 0. So we don't have to write them here at all. Plus 1 time theta 3. Plus 1 time x1 squared. Theta 3 is 1, sorry. Plus 1 time x2 squared. Right? And this needs to be larger. It's the same as here. It's always the same. And it's also the same as here, right? So we use this idea and we project it here and we do the same. We do the same here. Okay? It's the same idea. It's always the same idea. We just look at the function and see what kind of values do we need to look for. Okay, and then we get this equation, and as you know, this is like sort of the square equation. This is like the equation of a square, right? So, and then we can just like draw it like this, and we also can, like, this is an example of a more complex thing, right? Of a more complex decision boundary. And now you ask, your burning question is, how the hell do I know what to add? Plus in the chat if this is your question right now. How the hell do I know what to add? I mean, the important thing is that you do not ask, how do I know what theta is? Because this you don't have to care about. These are the parameters that are trained by the model. This is not what you should ask. If you ask yourself now, how do I know how to set these values? Then you did not understand how machine learning works. Because these values we don't have to care about. Our machine learning training takes care of finding these values. But what do we have to take care of? And now your questions in the chat. Your burning question. What's your burning question now? Like when you look at all this confusing and even look at this right here, like what are your burning questions? If I would to task you now to come up with such a decision boundary, right? What would be your question? Let's use this decision boundary where you can definitely not know the equation, right? Of this. Now, for this, if you paid attention in math, you could probably do that. But for this, what would be your burning question? Now, if I give you this in an exam and I say you can ask me one question to help you solve this, what would be your question here? Now, one information I can give you. What would be the information? If I say, hey, you generate a logistic regression model that generates this decision boundary, what would you ask me? It's very important. This tests all your understanding of machine learning right now. Think about it. I'm going to tell you, but yeah. And I did this on purpose. We purposely set these parameters, but no, in real life, these parameters are trained by the machine learning algorithm. I will never have to take care of them. I don't need to know these values. This is the difference to explicit programming. I do not need to know these values. So these are just examples. This is why I write down assume trained model. Right? So what is your question? So if these parameters get trained, what is your question? Okay, let me rephrase it. Okay, I'm gonna show you this in an exam. So we're gonna make an exam task. Task 4. Write down the hypothesis for the following decision boundary. Try to copy this one. Doesn't really matter. If I give you that task, there's a spoiler. You cannot. You simply cannot answer this without asking me a question. And it's not that I can answer it either, but I could look it up for you. But what is your question? If this is my question, I say, hey, uh, ask me one question. Or ask the internet or ChatGPT one question. What would you do? Look at this. So if this is the task, and I'm gonna like split screen this a little bit, it's very crucial that you think about this. What can't you know? How many parameters do we need? Okay. Let's try this. How many parameters? Okay, first question. Number of parameters. Okay. Um, I'm gonna say 5. Now, can you now write it down if I say 5? I'm gonna say 5. 5 parameters. Can you write it down now? No problem. You asked me, I'm gonna say 5. I'm saying 5. 5 parameters. Like this is I like the way everybody's thinking now, but this needs to come from you. You need to get this aha moment. You need to get it right now. No, we assume this task. I'm just asking you one question. Write down the hypothesis for the following decision boundary, right? Write down the hypothesis for the following decision boundary. Um, oh, if you assume, yeah, assuming that the model will be trained. Yeah, of course. Yeah, but that doesn't really matter. Like the thing is, I want to know the hypothesis, right? The hypothesis. So, um, this was the first question. So I can write, okay, assume training will occur later. So you don't have to obviously fill out the parameter values. Like you just put in the parameters as this. Okay. So, what is the format of the function? Yeah, that's pretty close. Okay. The 0, the 1, 1, the 2, 2, the 3, 3. Now, you assume this M, but the real question is, how would you know this, right? So yeah. So it gets more closer to the thing that Gina says, where she said, okay, what's the format of the function? So yeah, format of the function. Format. Um, the basic idea is actually what are our features that we use? What are the features that we use? Because nothing more is it, right? So, and then I will tell you format features that we use. I will tell you, okay, the features that we use are like, we use a constant, right? So we use obviously a constant. So number of the features that we use. And I say, for example, we use x1 times x2 squared, right? So, and this is why I could also say, hey, we don't use, for example, and this is why you can't do it based on a number of parameters, because we might use this, and we might use this, and we might use this, right? So this is theta 1, this is theta 2. Oh, sorry, this is theta 2. This is theta 3. We have theta 0, of course, right? So the important thing is what kind of combinations, what kind of squares, what kind of things do I enter here? This is what I need to select. And this is the clue here. Now, we don't need to take care of these parameters. We don't need to know them, but we need to know, what do we put in? Do we put in x1 square? Do we put in x1 times x2? Right? So if I just say 5 parameters, what does that mean? Right? Like here, we have like x1 square, x2 square, but here we also have x1 to the power of 3 times x2. You see this? It doesn't always have to be like fully staffed. So just because we have x1 squared doesn't mean we have to have x2 squared in it, right? So it's something we decide. Like, for example, we don't need x2 squared. Like we could also have just x3 here as it is without any squaring. And then but we could have x2 to the power of 3 times x3. And x3 never gets squared, right? So we have to decide what kind of features go into the model, right? So basically, I want you to imagine it like the following. Like we do feature engineering. Now we have our features. In this case here, we have x1, x2, and x3. And they come from the data. We have them in our database. Everything is fine. This is what we have. We have nothing more. Of course, we have a y variable. Yeah, of course. But now I want you to think of this as feature engineering, right? And now we decide what to add. So for example, we decide to add x2 squared. We decide to add x2 squared times x3. We decide to add x1 times x2 squared, right? And so on. We decide that. This is basically if you think of this as a feature engineering step, that occurs before modeling, it's way easier for you, right? It's way easier for you. So basically the question would be, what kind of features do you want? What kind of features give us this decision boundary, right? What kind of features? Now, of course, in real life, you will not like look at a decision boundary and say, oh, we need these features. So this is just to show you that we don't have to take care of the parameters, right? But we have to take care of what's behind the parameters, right? So the parameter, this comes from machine learning, right? But the weird combinations here, right? This comes from us. We need to determine this, and we can do this. Okay, so this is fairly important, right? And this comes from us only in shallow machine learning. So I can tell you in deep learning, I'm gonna make a function around this, right? I'm gonna make a function. In deep learning, I'm going to call this feature. I'm just going to call this new feature. New feature. New feature could be x1 squared times x3. Don't get me wrong. Just going to call this new feature. Comes from machine learning. And this also comes from machine learning. So this might sound, hey, this is pretty cool. So why are you teaching us this shit where we just have to decide? And why do you ask us all these questions? Because deep learning for that has other downsides. So here we have to configure way more of the algorithm. So for example, we have to say how many hidden layers do we want, the architecture, and so on. So everything, the architecture in deep learning comes from us. Comes from us. And it's way more complicated than just putting in like x1 squared. However, at some point, we move to deep learning because we cannot do this with shallow machine learning anymore because we have so many features, we have images and so on. So the trade-off at some point will be going towards our direction. Yeah, perfect. We've done it in time. We've finished it up. So last but not least, we're just gonna look at the cost function. And I just want to quickly go over this, but it's pretty easy. So when we train the logistic regression, can we use the old cost function? No, we cannot use the old cost function. Why? Because the old cost function is not convex, and we're going to end up in some local minima like this. And we need to make it convex, so we cannot use the old function. So basically, it's pretty easy. We apply a new cost function that does exactly the same thing, right? It does exactly the same thing. It compares the values that the original values to our values, right? To our values. And here, this we will summarize at the beginning of next week. Then we will go into exam preparation and some evaluation. And I will record the evaluation lecture for you, right? So this will be a recording available on demand because we will not be able to do everything next week. So this is why I will record this so you have enough time, and I will probably finish this by next week. An important thing, some of you were writing me mails say, I don't know how to prepare for the exam. So I took the weekend and prepared an preparation exam. It's online. You can do this many times as you want. This will be the difficulty will be the same in the exam, and the question types will also probably be the same. We will of course talk about this next week. So I hope to see you next week in the exam preparation. Plus, of course, we will finish up logistic regression. Plus, check out the new video on demand. It should drop at least at the beginning of next week. So you can also watch this. I will summarize it, of course, next time. There's not really much to it. It's pretty straightforward. It's pretty easy. And yeah, we will finish up the logistic regression. Then we will go into exam preparation. Don't forget, please, to read the exam information. And don't forget, if you have questions in your preparation, to ask them, right? So it's fairly important that I can prepare a little bit for the exam preparation. So it would be cool if you like, look at the dates when to send me questions. That would be pretty cool. And then I will answer these questions. I will make slides for each question, and then I will try to answer them elaborately in the exam preparation. So I hope to see you next week. We're finishing up the logistic regression. It takes about 10 minutes. It's not that different, the cost function, but we need to understand why we need a new cost function. So it will approximately take 10 minutes. And then we will go straight into the exam preparation. And don't forget, I will write the mail once the evaluation part drops. It will be part of the exam. But unfortunately, we missed one lecture because I was kind of sick. So we need to like cramp it in there. But it's a fairly easy topic, and you can understand it very well. Okay, thank you so much. And as always, your questions are very welcome right now. Thank you. See you next week.